In this video, we're going to go through a summary review of the basic formulas that you would need in thermodynamics for your first year thermal physics. So let us start with the first law of thermodynamics. Now, we said that the first law of thermodynamics is given as dq is equal to du plus or minus dw. Now, what is dq? dq actually stands for the change in heat or a quantity of heat that might be supplied to a system under analysis. And basically, dq could be also rewritten as ncp dt. You could also rewrite it as TDS. This is in terms of entropy. So if you have entropy changing within that system which is under investigation, and you have the time being constant, then the change in heat would basically be equal to the temperature multiplied by the change in entropy. Now du, that is going to be ncv dt. Now, what is Cp? Cp is a heat capacity at constant pressure. So the P, which is there, actually does stand for the pressure over which that heat was performed. Then we have Cv. This is actually the heat capacity under constant volume. Then we have dt. dt is basically the change in temperature, which is going to be T2 minus T1. So that is basically the ones that we have for D. Now dW, that is equal to P dV. Now we know that PV from the ideal gas law is equal to nRT. So if I took P dV, then I'm going to differentiate the variable which is present on the other side, which is the temperature. So this will be nR dt. So I could represent P dV as nRT also. So let us write that here. So this is basically an equation for the work done in a thermodynamic situation or for gases which are involved in heat. Okay, that means I could actually rewrite the first law equation in this way. This could be rewritten as ncp dt, and that will be equal to ncv dt, and that will be plus p dv. Now I could also rewrite it as I think I need to wipe out some stuff here. So this is ncp dt, and this is equal to ncv dt, and plus we have nr dt. So this is another way that you could actually write the first law equation under thermodynamics. Now you need to know that it's very possible for us to factor out n and dt and cancel them out. And if I did that, I would actually have Cp is equal to Cv minus R. Or you could also say that R is equal to Cv. So that is actually a mistake on my part. Let me rewrite this. This is actually supposed to be a positive. So R should be equal to Cp minus Cv. So this is one very important equation that you need to know. And you also need to be aware of this one. Then we're also going to talk about this one. So these might just well be the basic formulas that you need to know under first law. Now let us go to other thermodynamic processes, adiabatic process, isothermal, the isobaric, and so on. Then we would actually see the formulas that are derived or are very needful under them for you to solve questions under thermal physics. for an adiabatic process, this is actually a process that occurs or takes place under constant heat. Okay, so we know that heat is written as dq, and this is equal to 0. So that means if you have dq and this is equal to du plus dw, and dq is equal to 0 as a result of the fact that we are dealing with a adiabatic process, so this will be 0, and this is going to be du plus dw. So you just need to know that under a adiabatic process, you could have du, well, should write a u there, it could be equal to negative dw, or du, which is equal to n cv dt, could be equal to negative p dv. Could also be in this form. So you could also have nr dt. Okay, so that is just what you need to know for the first part of the adiabatic process under the first law. Now let us look at the equations that are actually derived under adiabatic processes. So for an adiabatic process, we have three main equations for the relationship between pressure, temperature, and the volume that are actually derived under adiabatic process. So the first one is P V raised to the gamma, and this is equal to constant. That means the pressure multiplied by V raised to the power of gamma, that is constant. So what that means is P1 V1 to the gamma is constant, and P2 V2 raised to the gamma is also constant. So basically we're just going to combine this because K is the same thing as K. So we have a P1 V1 raised to the power of gamma, and this is equal to P2 V2 raised to the power of gamma. And as a matter of fact, we could actually have it for P3 also, which is actually a rare case for basic physics. But you just need to know that as far as we have these combinations to be constant, you could actually take them to whichever extent that you want to take them. Okay, so this is the first equation that you have for that. Now, what is the value of gamma? This is actually called the gamma ratio. Now, the gamma ratio is equal to the heat capacity at constant pressure divided by the heat capacity at constant volume. Now, the heat capacity at constant pressure is going to be equal to 5 divided by 2 multiplied by R for a monoatomic gas, and Cv will be equal to 3 over 2R for a monoatomic gas. So you need to know that as we go on from the monoatomic onto a diatomic, you just keep increasing these numerators by 2. So that means for a diatomic, we should have Cp equal to 7 over 2R. And for a diatomic, Cv will be equal to 5 over 2. So that is basically the form of increase that you have. You could also have it for a triatomic. And so for a triatomic, Cp will be equal to 9. And that will be 9 over 2. And Cv, that is going to be 7 over 2R. So that is basically how you could go ahead and find the gamma ratio for an adiabatic process. Now you need to bear in mind that this is just one of the formulas. What is going to be the next one? So we have the next one is a Tv raised to the power of gamma minus 1, and this is basically equal to K. So you already know what it is. This means that the temperature multiplied by the volume, which is powered to gamma minus 1, is actually constant. So as you know, we should have T1 V1 raised to the power of gamma minus 1, and that would still be the same thing as a T2 V2 raised to the power of gamma minus 1, right? That actually continues to whichever extent that you have available in that question. So this is the second equation that you need under a adiabatic expansion. Now there is actually one more, which is the combination of pressure and temperature. Whoa, so I need to rewrite this one. Now, I actually made a mistake. Oh, so this actually has to be 1 minus gamma, and you're going to have a t raised to the power of gamma here. This is equal to k. So this is what you have for the third. Now that basically means that you could have p1 raised to the power of 1 minus gamma multiplied by t1 raised to the power of gamma, and that will be equal to p2. So you could have this 1 minus gamma multiplied by t1 raised to the power of gamma. This could be equal to p2 raised to 1 minus gamma multiplied by t2 raised to the power of gamma. So that is basically what we're trying to say. Now, one of the last things that you need to know under a diabatic process is actually the work done under an adiabatic process. Now, what is the work done under an adiabatic process? How is it written? So this is basically what you have. You have W, and that is equal to NR divided by 1 minus gamma, and this will be into T2 minus T1. So this is basically what you have. But you could also have it in another form. You could have it as 1 divided by 1 minus gamma, and this is going to go back inward. And so you already know that we have PV to be nRT, right? So if we have nRT in the first case, that should be P1 V1, and if we have nRT2, that should be P2 V2. So I'm just going to use that to replace stuff here, and that will give us a P2 V2, and this is minus P1 V1. So that is basically what we have. Okay. So that is basically it under the adiabatic process. Now let us go on to the isothermal process. Now for the isothermal process, you actually have stuff or the process actually occurring under constant temperature. That means dT, that is equal to 0. So we know that du, which is the internal energy, is equal to NCV dt. Now, what actually happens is that if you have isothermal processes, those processes actually take place in a situation where you could only substitute du as NCV dt. Now, dq was actually said to be NCP dt, but you don't actually get to use this one because this is actually under constant pressure, which is not allowed, okay? Because the pressure is not constant, and so because of that, you're not actually going to use this. So we just use this one. Now we know that dq, that is equal to du plus dw. So this would be dq, and this is going to be equal to NCV dt, and this is plus dw. We know that dt should be equal to 0, so dq is going to be equal to 0 plus what? dw. Now as it is, under an isothermal process, you should have dq equal to dw, right? So this could be also rewritten as a pdv or as nrdt. So this is basically the transformation of the first law equation under isothermal process. This is basically what you have. Now let us look at the work done under an isothermal process. So this is what we have. We know that work done is written as W, and that is equal to nRT. You have ln V2 over V1. So this is what we have. Although it's actually very possible to change the natural logarithm and use the basic logarithm. And by doing that, we should have 2.303 nRT. And that now will be a logarithm to the base 10. And then we're still going to have a V2 divided by V1. Now, we also know that from the Boyle's law, P1 V1, that is equal to P2 V2, right? So if I divided both sides by, let's say, V1 here, and then let's say P2 here, that is going to give us something very interesting. So let me clear this one out and rewrite it. So this is a P1 V1. This is divided by, let's say, P2, and this is going to be V1. So we are basically dividing both sides by this stuff. Now P2 cancels out, and we're going to have V2 divided by V1. V1 also cancels here. So basically what we have is V2 over V1. And this is equal to P1 over P2. So what that basically means is that you could also replace the ratio of the final volume to the initial volume if you have the initial and the final pressures. So it's possible to write these also this way. So this will be P1 over P2. Just take note of the inverse relationship that there is always going to be there. You could also write it in terms of the general logarithm, which would actually introduce a 2.303 and a log to the base 10 there. So that is basically what you need to know under an isothermal process. Sorry, a work done under an isothermal process. Now let us move on to the next one. So the next one, that is going to be an isobaric process. Now, what is an isobaric process? This is basically a process that takes place under constant pressure. So what that basically means is that dP is equal to 0. Now, is there going to be any change in the first law equation? So the first law equation, we have a dq, and this is equal to du plus dw. So for dq, we have ncp dt, and for dw, we have ncv dt. Well, this is du, not dw. Now for dw, we have a p dv. As you can see, there is no quantity or any term that has a dp there. So that means under isobaric processes, the first law equation remains the same. That means dq, that will still be equal to du plus or minus dw. So that is basically it under the first law. Well, what will be the work done under an isobaric process? So for an isobaric process, the work done is basically P dV. Now we know what dV is. dV, that is equal to the change in volume, which will be V2 minus V1. And so this is basically it. If you know what the constant pressure is and what the two volumes are, you could actually take the change in the volume and multiply with the pressure, and that will still give you the work done. Now, we also know that P dV is the same thing as nRr dt. So this could also be used. This is going to be T2 minus T1. I think I need to rewrite this one. So this is basically what you have, and it could also work because this is equal to this. Now the very last formula that you need to be aware of is under heat engines. Now for heat engines, you basically talk about the efficiency of those machines. A heat engine is basically a machine that uses heat to do work. So what is going to be the efficiency of heat engines? So the efficiency of a heat engine could be written as this, and this is equal to the work output divided by the work input. Now you could also write it in terms of percentage. And if you want to do that, you will just multiply the answer by 100%. Now what you need to know is that for every heat engine, none can actually work up to 100%. That means there is actually no heat engine that is perfect. So all heat engines would always work below 100%. That means this value, or this ratio rather, would actually be a ratio that would always be less than 1, because 1 is 100%. And so that doesn't work. Okay? Now, we could also write this efficiency in another form. You could write it as the change in quantity of heat supplied divided by the quantity of heat. Now, instead of writing that, let me use this statement. Let us say that this is actually the heat at the hot reservoir, and minus heat at the cold reservoir. Now, what do I mean by all these statements? Well, this is actually going to be divided by the heat at the hot reservoir. So this is basically what we mean. If you have a heat engine like this, what actually happens is you would actually have the hot reservoir, which I may just write it to be this one, and then there is also the cold reservoir, which is this one. Now heat is actually going to be used to perform work. Now as the heat is used to perform work, as it transmits from this hot reservoir, which I would actually write as Q1, because obviously, as you already know, heat should move from the hot reservoir to a cold reservoir, which is basically reasonable. Stuff would always move from the hot region to a cold region. So this should be Q1 and this is going to be Q2 to represent the cold. That means the amount of heat that there will be here is actually going to be greater than the amount of heat in Q2. Now, as this heat is being transmitted from Q1 to Q2, work is actually being done. Okay, so what that means is if you talk about work output would actually be Q1 minus Q2, which is the same thing as this stuff that is written here. So this is going to be efficiency, and that is going to be Q1, which is the heat at the hot reservoir, minus Q2. And this will all be divided by Q1, which is still the hot reservoir. Now that is reasonable because efficiency of a machine can never be greater than 1. In fact, we cannot actually have it up to 1. Okay. Now let us look at some stuff. If you have N, and this is equal to Q1 minus Q2 divided by Q1. Bear in mind, Q1 would always be higher than Q2. I could split this, and this would give me Q1 divided by Q1, and that will be minus Q2 divided by Q1, right? Now, we know that Q1 divided by Q1, that should give us 1. And this will be Q2 divided by what? Q1. So this is one equation that you really need to bear at the back of your mind as we solve questions under heat engines. But there is actually one more that you also need to pay attention to. Well, yeah. So which is that one? Now we know that Q, which is the quantity of heat, is basically equal to mc dt, right? Or if, well, so that should actually be written this way. I should actually write it as dq is equal to mc dt. That is the mass multiplied by the specific heat capacity and multiplied by the change in temperature. So if I wanted to take out the differential form, this should basically be Q, and that will be equal to mct. Now, mass of a quantity is always going to be a constant, and the specific heat capacity of a material would always be a constant also. So if I said Q1, this is going to be mct1. If I talked about Q2, that is going to be mct2, right? So let us work with that. I'm going to write Q2 here. This is equal to mc of T2. Now, we already said that the efficiency of a machine is Q1 minus Q2, and that is divided by Q1, right? So we know that Q1, that is the same thing as mcT1, and this will be minus mcT2, and this is divided by mcT1. Now, as you know, we could actually factor out m and c. So this is mc, and this will be T1 minus T2, and this is divided by mc T1. So mc cancels out, and we have a new equation for the efficiency of a machine, or an engine rather. So this is T1 minus T2, and that is divided by T1. Or you have 1 minus T2 divided by T1. So this is one other equation that you also need to hold very well at the back. So having got this once, we're actually going to go into solving questions. And we will basically deal with questions that are involved with all these formulas, which we have actually listed out in this first part of the video. So let's jump right into it.